Good afternoon. This is part two of our kind of secrets to success live sessions, if you like, for Chemistry Coach here on YouTube. So welcome. So yesterday we were looking at titrations and the calculations and errors and all things kind of titrations really, but pracs in general as well. And we also looked at bonding. So how to go about answering bonding questions, how to get all the marks in bonding questions and making links and things like that. We talked about identifying the type of bonding, describing the type of bonding, and then explaining the differences in physical properties, whatever that might be in the question. And that's how you organize your answer to get all the marks. So, a really good session yesterday based on like the classic types of questions you get, not just for AS, but also for A-level students as well, because bonding and calculations, titrations, of course, do appear again in AS. They can appear in questions, okay? Thinking about it, actually, the most common AS topics that come up in A-level papers are calculations, of course, bonding and enthalpy. They're the big three, really, Hess's law and stuff like that come up, during A-level. So today we are looking at another two areas of chemistry which are super important. Those two areas are atomic structure and linking atomic structure around to different topics. So this is very much the first part about using your knowledge in atomic structure and helping you apply and kind of just make insights really to help you with more difficult questions in other areas. So we're linking atomic structure to all sorts of other areas and why that's so important. And the second part we're looking at today are organic mechanisms. A lot of the time, you see these social media posts by students, ex-students, whatever, saying, know your mechanisms, learn your mechanisms. Yes and no, okay? The important thing is that you really understand those mechanisms and how they work, okay? So that's super important. So in respect of today's session, we're going to be looking, like I said, at atomic structure and then, of course, on to the mechanism side of things. And they'll kind of work into each other quite seamlessly. That's the plan anyway. But in the meantime, you'll see this kind of scooting around down at the bottom. If you want to get ahead and you want some really super reliable exam board specific notes, then head on over to chemistrycoach.co.uk for AQA, WJC and OCRA. You can access those notes for free. They're totally searchable. You can add your own little post-it notes to them and add things to do and stuff like that. So you can access those for free. But if you're a Chemistry Coach member, you get so much more. So let's just dive in, shall we, onto atomic structure and the importance of atomic structure. I'm just going to have a sip of coffee. 1 second. Okay, so let's just remind ourselves about the trend in atomic structure in the periodic table, and then we're going to link that to loads of other topics and why it's super important to understand how atomic structure affects other things. And like I said, the idea here really is to help you kind of apply some, dare I say, common sense to more complex questions in other areas in chemistry, and why the other trends and things just make sense. The thing here as well is that rather than learning a hell of a load of trends, you can just work them out there and then, just by using this kind of simple application of the knowledge of atomic structure. And by atomic structure, I don't mean like 1s2, 2s2, and so on and so forth. That's electronic structure. We're talking about shells, we're talking about nuclei, we're talking about shielding, okay, all that sort of stuff. So I am live. Hey, hello, I am live. So hopefully that proves it. So this is obviously being recorded, so if you want to watch it another time, that's absolutely fine. But right now, I'm with you, you're with me, and we're going to hit this, okay? So let's go straight into this. So this is obviously blank periodic table here. So let's just talk about atomic structure, generally speaking, in the periodic table. So obviously in terms of atomic structure, we're talking about the nucleus, and then of course we have got our kind of shells that kind of go around it. I don't know why that's a dotted line, but we'll go with it, okay? So of course, what we want to do is think about how atomic structure relates to the different trends in the periodic table and helps us actually get to grips with and kind of on the fly kind of figure out exactly what is going on with all sorts of other areas in chemistry. Oh, thanks, A. I've been described as many things. A goat. That is awesome. Thank you very much. And it seems like you're on TT, which is great. Okay. Yeah. So I'm really pleased you think more people need to know about me. I'm really, really, really quite pleased about that. Thank you so much. So trends in a periodic table. So I will be asking questions as we go through. So feel free to answer in the chat and stuff like that. So as we go down down any group, okay, what's happening to our atomic structure is that our atomic radius, okay, is increasing. Okay, so excuse the rubbish drawings here, but our atomic radius is increasing as we go down. Why? Because we're adding a full shell or full energy level of electrons every time we go down that period. So atomic radius increases going down the periodic table. Okay, so atomic radius increases. We know this. I'm not going to go into detail on that. It just makes sense. Question for the chat though, as we go from left to right across a period, what's happening to atomic radius, ladies and gentlemen? Increases, decreases, stays the same. What is it? As we go from left to right across any period, what happens to our atomic radius? Answers in the chat would be great. I want you guys talking to me a little bit here. Increases, decreases, so on and so forth. Hafiza, increase in atomic radius. Atomic radius decreases because nuclear charge increases. Yes. Okay, so the answer is, sorry Hafiza, the answer is decrease. The atomic radius decreases going from left to right. The reason is that as we go across a period, let me just do that again, the number of shells that we have stays the same. So the atomic radius for every single atom going across here, okay, is very, very similar, okay, very, very close, because we're not adding energy levels of electrons, we're just adding an electron. And then it's at the end here, this is where that energy level of electrons is full, and that's when we have to add a new one in the next period. Okay, so we're not adding energy levels, so it's not getting any bigger. The reason it gets smaller, and A, you're absolutely right, is because nuclear charge increases. Okay, so what we say is atomic radius decreases. That's because we have an increase in nuclear charge, because of course, every time we add an electron, we're adding a proton as well. So that charge on the nucleus increases, but the number of shells or number of energy levels stays the same. So what actually happens is, let's say we do have two elements side by side. So let's just pick, I don't know, carbon and nitrogen, for instance. Okay, carbon and nitrogen are next to each other. Because they both have the same number of shells, nitrogen has got one more electron, so it's got 7 protons, and carbon's got 6 protons. The reason why it's slightly smaller as you go across is because the nuclear charge increases and just draws those electrons in much more closely to the nucleus. Okay, so while we're not, and making sure you say this, the number of orbitals or number of shells stays the same, but the nuclear charge increases, so it draws those in closer. Okay, draws those in closer, and that's why we get a decrease in atomic radius from left to right. Okay. So that's the one trend that we're always going to be looking at, okay, is the atomic radius, the trend in numbers of shells, okay, and the trend in proton number, so the trend in nuclear charge as well, okay. So they go down as you go across the period. So let's get into some other areas where this is important. Number one is ionization energy. We all have to do first ionization energy, so let's just clear the decks here. So talking about first IE, let's just get rid of these. Let's get rid of that as well. Why not? Get rid of these. Okay, so answers in the chat. As we go down a group, first ionization energy, what's the general trend as we go down a group? Okay, and we're going to link this to atomic structure. So what's the trend in first ionization energy going down a group? Does it increase or decrease? Does it take more energy to remove that electron, which is increase, or does it take less energy to remove the outer electron? In other words, decrease. Good, Hafiza, thank you. Decrease. Okay, so we get a decrease in first IE. Okay, so a decrease in first IE as we go down the group. Now, the reason is, as we should all know, as you go down a group, the atomic radius increases. That means the distance from that of the outer electron from the nucleus also increases, which means there's less of an attraction between the nucleus and that outer electron because we're adding all that shielding of electrons in between. So it makes it easier to remove the outer electron because shielding increases, the distance of that outer electron from the nucleus increases. So that nucleus, even though we're getting more protons in there as we go down, the shielding is the star of the show. That's what causes a decrease in first ionization energy, regardless of the fact that your proton number, your number of protons in the nucleus increases, okay? Oh, no worries, my pleasure. This is probably worth you hanging around for, but if you, on Wednesday and Thursday this week, I'll be doing A-level topics. So tomorrow and Thursday, I'll be doing A-level topics if you want to pop back then, okay? Thanks for coming. So, as we go from left to right now, okay, we do have a general increase in first ionization energy, okay? And we say general increase, okay, because there are some blips on there. It goes up, then it comes down, it goes up, then it comes down, then it goes up. We have these blips here, we have these, but why is there a general trend in first ionization energy to increase going from left to right? Well, the same reason as before. The number of protons increases, okay? So the nuclear charge increases going from left to right. However, we are keeping the same number of shells. We're not adding any shielding. So we get that general increase because there's an increase in nuclear charge, no increase in shielding. So that's why the attraction between the nucleus and the outer electron actually increases, okay? Oh, I seem to have lost my iPad there for a second. Never mind, we're back now. That's all good. So again, it's atomic structure that dictates the trend in ionization energy. You do need to know these exceptions, by the way. I'm not going to go into those today, but just remember the reasoning behind this change in atomic radius and first ionization energy. We're always talking about the same three things: the strength of the nuclear charge, the amount of shielding, and what comes hand in hand with that is the distance from that nucleus to the outer electron. Okay, so just think logically, remember your trends in atomic structure. That will help you basically remember the explanation for these trends in first ionization energy. So one more time, down the group. Okay, we've got increased shielding, increased distance between the nucleus and outer electron, therefore a weaker attraction between the nucleus and outer electron, and that's why it's easier to remove it. Going from left to right across a period, we have got shielding, which stays the same. We've got an increase in nuclear charge, so therefore the attraction, generally speaking, between the nucleus and the outer electron increases, and that's why it requires more energy to rip an electron away from the atom. Okay, so remember that. All right, the things that we're talking about: nuclear charge, distance from the nucleus, and amount of shielding. Now that explanation should be kind of ingrained there, kind of carved in stone in your grey matter, because first IE questions come up every single year, whether you're AS or A level. Okay, so super, super important you know that. Now those explanations aren't just limited to first ionization energy, are not just limited to first ionization energy. So atomic structure has so many impacts in so many other areas. So we've looked at atomic radius, we've looked at first ionization energies, okay, and the reasons for that. Let's see if we can link that to something else now. So I'll just list these at the bottom actually. So we've looked at atomic radius, we've looked at first ionization energy, and the things that we've used, the explanations that we've used, let's put these in red down the bottom here. We've talked about nuclear charge, we've talked about distance between the nucleus and electron, and we've talked about shielding as well. So these three things, okay, if we can apply those to these other areas, that means we don't have to remember other trends, okay? So Onwards and upwards. What's next, ladies and gentlemen? Let's talk about oxidizing power. Okay, let's not forget oil rig. Oxidation is loss of electrons, reduction is gain. Now, where this really comes into the fore in A-level chemistry, as far as the periodic table is concerned, is group 7. So, of course, we've got fluorine, chlorine, bromine, iodine, and astatine. Okay, and obviously we've got tennessine at the bottom there, but we never talk about astatine or tennessine. Okay, but let's just focus on these ones here. So, what we need to think about is the redox power of the halogens and the halides. Okay, so our halogens, are they oxidizing agents or reducing agents? Have a think about that carefully. Put the answer in the chat for me. Are halogens oxidizing? So just fluorine, chlorine, bromine, and iodine. Are they oxidizing agents? So do they cause other things to lose electrons? Or are they reducing agents where they donate electrons to other things? So what are they, the halogens? Oxidizing agents or reducing agents? Any takers in the chat? Are our halogens oxidizing agents or reducing agents? No takers? Fair enough. Halogens are oxidizing agents. Okay. So what they do is, let's say you've got fluorine here with 1, 2, 3, 4, 5, 6, 7. You've got 7. Thank you, Hafiza. What it's doing is, or all halogens, they are accepting electrons from other things. Okay. I don't know why my iPad's being weird. Oh, tech let me down again. Come on, iPad. One second, guys. There we go. We're back in again. Dodgy connection, I think, in the wire. Okay, so halogens are oxidizing agents. Which is the most powerful oxidizing agent out of our group 7s that we've got here? Fluorine, chlorine, bromine, iodine. Okay, which is the most powerful oxidizing agent? The most powerful oxidizing agent is fluorine. Okay, at GCSE we were like, it's the most reactive. All right, but it's the most powerful oxidizing agent that we have in terms of our group 7s. Now, if you think about the reason for that, to be a good oxidizing agent, fluorine needs to be really good at attracting an electron towards it. Okay, that's what makes it a good oxidizing agent. When you look at the atomic structures of fluorine, of chlorine, I'm running out of room here, of bromine and of iodine, it's quite clear why fluorine has the most, or is the most powerful oxidizing agent, because fluorine has the least amount of shielding. Okay, it has got a, the smallest nuclear charge, fair enough, but because it's got a very small amount of shielding, because it's a very small atom in terms of atomic radius, it's really good. If an electron comes past fluorine, it just grabs it. It's like, that's mine. Okay, the electron's really attracted to it. So fluorine, that's why it's a really good oxidizing agent. Whereas iodine, okay, down here, iodine is rubbish at attracting electrons towards it. The reason being because it's got a large atomic radius. It's got lots and lots of shielding. Even though it's got more protons, because of all that shielding, just like in first ionization energies, it's rubbish at attracting electrons towards it because of all that shielding. So knowing your atomic structure, okay, and the trend in atomic structure, it just makes other trends make sense. So in terms of an oxidizing agent, fluorine is the best because it's got a low amount of shielding, it's got a strong attraction between the nucleus and whatever electrons coming past, it attracts it really, really strongly. So that's why it's a really good oxidizing agent. And on the flip side of things, iodine, absolutely pants oxidizing agent because of all that shielding. An electron flies past, it's just like, meh, it's just too far away. I've got way too much shielding. I can't be bothered attracting that electron, okay? Because the attraction between the nucleus and that passing electron is really, really weak. So that just makes sense, okay? So halogens are oxidizing agents. So what does that mean for our halides? Okay, our halide ions, okay, like F minus, Cl minus, Br minus, I minus, this is where they've already gained an electron. So F minus, for instance, would look like this. Okay, so there's the extra electron I've put as a circle. All right, so now if we consider our halide ions that do have a full outer energy level of electrons now, okay, they're relatively happy. But what I'm thinking is, okay, well, if halogens are oxidizing agents, halides must be reducing agents. Because just because they've gained an electron doesn't necessarily mean they can't let go of it again. All right, so halides are reducing agents. They are agents that give an electron to another species to reduce it. Okay, so they donate an electron to another species which gets reduced. So halides are oxidizing agents. They can be reduced themselves. So let's think about this. If we've got these structures that I showed you down here, terrible drawings, I know, okay? But of course, the amount of shielding is, as you go down the group, increases. So bearing in mind what we said before, you've got fluoride, you've got chloride, you've got bromide, and you've got iodide now. So this circle that I'm putting in is the extra electron they've already got. Which one is going to be best at losing that electron again? Well, it's going to be iodine, because iodine, we know already, has the weakest attraction between the nucleus and the outer electron. So if anything's going to lose an outer electron again, it's going to be iodine, okay? So iodine is really good. If it has gained an electron, it's really good at losing it again. So it's kind of like, oh, you want this electron? Yeah, fine, whatever, take it. But it's just, you know, I'm struggling to hold on to it anyway because the attraction between my nucleus and the outer electron is really weak. So just take it. Just take it. And so iodine is really good at iodide, is really good at donating that outer electron and reducing something else. The reason being, for the same reasons as our ionization energy, increased shielding means there's less energy needed to remove that outer electron. Just because it's an extra one that it's had because it's been reduced itself doesn't make any difference, okay? So that explanation of first ionization energies comes in and explains why, first of all, fluorine is our strongest oxidizing agent, okay? Nuclear charge, shielding, distance, and why iodide is the strongest reducing agent, again, distance from the nucleus, shielding, okay? That's why. So all those explanations you learn for first ionization energies are the same reasons and explanations as to why we get the trend in oxidizing power of our halogens and the trend in reducing power of our halides. Because on the flip side, fluorine up here, or fluoride ions, once this fluoride ion's got this electron, it ain't letting go. So it's rubbish at being a reducing agent because it just won't give up the electron to reduce that other thing. Okay, so atomic structure, massively important. It helps you, not if you can't remember the trends, you can work them out using, dare I say, common sense in terms of the amount of shielding and the distance from the nucleus and so on and so forth. So that's how atomic structure helps you understand and recall those trends in oxidizing power of those different elements. And it's not just the halides. You can compare the reducing power of the oxidizing power of oxygen and sulfur. Okay, oxygen is a more powerful oxidizing agent than sulfur because, for the same reasons, fluorine is stronger than chlorine. Okay, because it's got less shielding, greater attraction between the nucleus and outer electrons, and so on and so forth. So they're the same reasons. I cannot stress that enough. Okay. Now, moving on. So that's the redox power using group 7s as a guide, okay? So let's get rid of those for a second. So we've done first IE, we've done redox power of group 7, okay? So that's that understanding there. Now, the next one on the list is electronegativity, okay? Now, firstly, so many students get the definition of this wrong, okay? So listen very carefully. The electronegativity of an element is, and I quote, the power of an atom, okay, to attract a pair of electrons in a covalent bond. All right, that's electronegativity. So, in other words, how good is that atom at attracting a pair of electrons in a covalent bond? If you have, let's say, two chlorines bonded to each other, they're going to share that bonding pair of electrons equally. The reason being because chlorine and chlorine, being the same element, have the same electronegativity. They have the same power or ability to attract that bonding pair of electrons. So they spend 50% of their time over here and 50% of their time over here, and they're shared perfectly equally. It's the same for any two elements that are bonded together like this. Okay, so if you've got the same element either side of a covalent bond, it's going to be a non-polar bond. Okay, those electrons are shared equally. However, if you get a difference in electronegativity, so let's say between hydrogen and chlorine, the chlorine is more electronegative, so that's why it's attracting that pair of electrons towards it. Okay, because it's more electronegative, it's better at attracting electrons. Now, where are our most electronegative elements? Generally speaking, in our periodic table, top left, top right, bottom left, where are our most electronegative elements, people in the chat? Where are our most electronegative elements? I'll allow for the delay here. So is it top left, top right, bottom left, bottom right? Where are our most electronegative elements? Yes, Hafiza, thank you. Fluorine is the daddy, isn't it? Okay, so fluorine is the most electronegative element, closely followed by oxygen and nitrogen. So these three are the kings of electronegativity. Okay, well, let's take I've got chlorine, bromine, and iodine down here as well. We got sulfur and phosphorus. Let's take PCl3. Okay, so PCl3, like so. I'll do the three-dimensional one. Okay, now of these elements, okay, chlorine is the most electronegative. So we're going to have slightly negative. Chlorine's going to get the lion's share of these bonding pairs of electrons. Okay, so that's where phosphorus and chlorine come in with each other. Now I know this because chlorine is more electronegative than phosphorus. How do I know that? How do I know that? Well, let's say we've got phosphorus and we've got chlorine. Okay, just get rid of that one. Sorry. They're both in the same group. It's both in the same period. All right. Now, why is chlorine more electronegative? Ask yourself, why is chlorine better at attracting this bonding pair of electrons between the two? Well, it comes down to atomic structure again. So, as we mentioned about atomic radius, why does atomic radius decrease? Well, the proton number, the nuclear charge, increases, but we don't have any more shielding. Okay, we're not adding energy levels of electrons. So the reason chlorine, or the reason why electronegativity, I'll just put this up here, electronegativity increases going across a period is because we're having an increased nuclear charge, but no extra shielding. So if it's got an increased nuclear charge, chlorine, compared to phosphorus, then yes, it's going to be better at attracting a bonding pair of electrons towards it. Okay, so again, the same reasons for first ionization energy, same reasons for redox power. It's about atomic structure. So increased nuclear charge, no extra shielding. That's why chlorine is more electronegative than phosphorus. That's why it's better at attracting a bonding pair of electrons towards it. Okay. Likewise, let's use FCl. Okay, we can get FCl, it's a thing. Okay, or FBr. Let's go FBr. Why not? Okay. Now, we know that fluorine is the most electronegative element. Okay. So it's definitely going to be delta negative, delta positive. Fluorine's going to have the lion's share of those electrons in this bond. Okay. So in terms of electronegativity, why is fluorine more electronegative than bromine? Well, fluorine and bromine, okay? So bromine increased atomic radius, increased distance between the nucleus and this bonding pair of electrons, increased shielding between the nucleus and this bonding pair of electrons. So fluorine, because it's got low shielding, okay, relatively low distance as well, it's really good at attracting electrons towards it. Whereas the bromine, that's less electronegative because of all this shielding it's got. That's why it's not very good at attracting a bonding pair of electrons. So that's why as you go down a group, electronegativity decreases, okay? Or you could say, let's do it the other way around, guys. As you go up a group, so we're all focused on fluorine here, electronegativity increases going up a group because the atomic radius gets smaller, there's less shielding, and that's why electronegativity increases, okay? So again, we're using atomic structure just to work out why things are polar, why electronegativity has the trends in the periodic table that it does. So hopefully that all makes sense. We're tying all these things together. They're all coming back to atomic structure, okay? So that's the other thing. So we'll put that in there. Electronegativity trends, okay? So that's why that increases. So let's extrapolate from there, ladies and gentlemen. I'm just going to go over the page here now. So if it affects electronegativity, okay, so atomic structure, a couple of notes here. Dictates electronegativity. That then dictates bond polarity. Okay, so the bigger the difference in electronegativity based on the atomic structure, the bigger the difference in electronegativity, the more polar a bond is. Okay, and the more polar a bond is, the weaker a bond is. Okay, so again, atomic structure dictates electronegativity, which dictates bond polarity, which dictates the strength of a bond. Okay, so the more polarized the bond is, the easier it's going to break because those electrons aren't being shared very equally. The one that is not getting the electrons is more likely to kind of leave, if you know what I mean, and that bond breaks. So atomic structure affects bond enthalpy as well. So bond strength, bond enthalpy, the amount of energy we need to break a bond. And it all comes down to, again, all the way back to atomic structure, okay? Speaking of bond polarity is really important when it comes to simple covalent molecules because bond polarity dictates the types of intermolecular force that we have. Our three types of intermolecular force in order of strength, strongest are hydrogen bonding, where we have to have hydrogen directly bonded to fluorine, oxygen, or nitrogen, okay? We've then got permanent dipole. So typically where we see like a CCl or a C double bond O, we're looking for those sorts of bond polarities there. And of course, we've got induced dipole or London forces. Some people call them van der Waals forces, all the same thing, induced dipole. So of course, atomic structure, this is why hydrogen bonding's a thing, okay? Because hydrogen bonding is basically just like a super dipole, all right, when you think about it. If you've got fluorine directly bonded to hydrogen, and fluorine being the most electronegative element, it's going to have, like, those bonding pair of electrons are going to be spending like 99% of their time with fluorine, okay, because of its atomic structure, because it's so electronegative. And if we think about what hydrogen actually is, it's just a proton and an electron. That's it. So hydrogen here is basically, in this bond, most of the time, just a naked proton. That's all that's there. If fluorine's got hydrogen's electron most of the time, it's just a naked proton. There's nothing there. So this ends up, this ends up being a super, super, super dipole, okay? And even though we still put delta positive, delta negative, that's why hydrogen bonding is so strong, and that's why it affects melting and boiling points so much. is because of that super polarized bond between the fluorine and the hydrogen, the oxygen and the hydrogen, or the nitrogen and the hydrogen, those three most highly electronegative elements and hydrogen. That's why hydrogen bonding is a thing. And of course, we got permanent dipoles as well. These are caused by a difference in electronegativity, which is caused by a difference in atomic structure. So atomic structure impacts not only bond polarity, but bond strength. And because of bond polarity, it also affects the intermolecular forces that are between the molecules. It is the root cause of those different intermolecular forces in the molecules. So we're making a huge link there as well, okay? So going back, electronegativity dictates bond strength. It also dictates bond polarity, okay? And therefore, because of bond polarity, it affects the type of intermolecular forces you get between molecules. So this is me linking atomic structure to everything. And again, it's all because of the amount of shielding, the distance between the nucleus and the outer electron, the atomic radius, okay, and essentially the attraction of that nucleus to either the electrons in the atom or the electrons that are passing by in redox, or indeed the electrons in a covalent bond if you're looking at bond polarity and electronegativity, okay? Now, the last thing I'll mention when it comes to dipoles, and again, difference in electronegativity causing dipoles and things. Without dipoles, okay, we would have no organic mechanisms. Every single organic mechanism you look at, okay, is because you have got a dipole somewhere, whether that's the dipole in a haloalkane, and then your nucleophile comes in and attacks this delta positive carbon, whether it's electrophilic addition and this pair of electrons is attracted to the delta positive hydrogen. In any mechanism you get these dipoles that kick the whole thing off, okay? So no dipoles. If everything was non-polar, there'd be no reactions in organic chemistry, okay? So atomic structure dictates electronegativity, which dictates bond polarity, which then allows us to kind of draw organic mechanisms. So even all the way through to organic mechanisms, that's where atomic structure has its impact, okay? But the most important ones for me in this list here, okay, are atomic radius. Our explanations for first ionization energy are the same explanations as for why we get a difference in redox power, and they're the same explanations as to why we get a difference in electronegativity. And then electronegativity dictates bond strength, bond polarity, intermolecular forces, and how and why mechanisms actually work as well. Okay, so that's why that's super, super important. But remember, your explanations for these trends are all the same. Okay, all the same. I cannot stress that enough. So rather than learning them individually, link them together. Chemistry A-level is like a spider's web, okay? They're not just separate and distinct topics. Like in biology, you get like, okay, we're doing gas exchange over here in humans and insects and fish and all sorts of stuff. Oh, and then look, we're doing photosynthesis over there. Absolutely nothing to do with, oh no, that's a bad example, because obviously plants undergo gas exchange, but by a different mechanism. But you get what I'm saying, okay? The link here is atomic structure. So, speaking of mechanisms, I should say, any questions on atomic structure here, folks? Any questions on atomic structure at all and how it links to other things? If you think there's another link that I've missed, maybe pop it in the chat. If you don't, then that's fine. But we're going to talk organic mechanisms just for the last kind of 10 minutes or so here. That's all. I'm going to go on a bit of a rant about how to really learn the organic mechanisms that you need to know. So any questions, then just do pop them in the chat for me, please, guys. Okay, so I'll assume not. Mechanisms next. So, there's all sorts of different mechanisms that you need to know. First thing I would say is that, let's state the obvious here. It might not be obvious to all of you, and I don't want to kind of assume anything here. but the names of the mechanisms are literally descriptive of what's happening. Okay, if you haven't made that link yet, that's a link. Okay, nucleophilic substitution. Well, there's a nucleophile involved, so something that's an electron pair donator. So a nucleophile either got a lone pair and sometimes a negative charge as well. So all you need is that lone pair for it to be a nucleophile. Substitution, well, we're substituting one thing for another. We're just swapping something out. So all these names of these different mechanisms are very, very descriptive. So let's think about nucleophilic substitution just for a second, okay? And let's think about the flow of a mechanism. So the flow of a mechanism is based on what's actually happening, okay? So let's take something very simple. So chloromethane, okay, like so. And let's say we're undergoing, this is undergoing nucleophilic substitution with aqueous sodium hydroxide. Now, mechanism's all about three things, okay? Number one, dipoles, as we've mentioned before, okay? Number two, curly arrows. And number three, lone pairs. Okay, so that's what they're going to be looking for, and charges as well. Okay, so dipoles, charges, curly arrows, and lone pairs. That's where all your marks are going to be coming from. Now, at home, whether you're watching this now or whether you're watching it later, don't just learn mechanisms. Yes, obviously, you need to learn them, but just make sure you understand exactly what's going on. Mechanisms are a story, okay? When two things react together in chemistry, it's not just magic, like it just poof, and all of a sudden they're new things, okay? There is a set mechanism for the process of that reaction taking place, okay? Even in inorganic chemistry, when you look at rates of reaction, most of you in your specs need to do the rate determining step. That's the same thing. It's the process of how the reaction happens. What happens first, then what happens next, and what happens next. This is us showing that in organic chemistry. So, of course, dipoles, as we've already mentioned, are basically caused by differences in atomic structure, differences in electronegativity. That's where we get dipoles from. So, if you get in the exam and you're just remembering, well, the C is delta positive and the Cl is delta minus, what happens if you have a brain fart in the exam? You just can't decide, and your brain pulls a trick on you, like, what is it again? Which one's the delta positive one? This is where your knowledge of atomic structure comes in, okay? Well, chlorine's more electronegative than carbon. So logically, our dipole needs to be this, because chlorine's going to have the lion's share of this pair of electrons that's in that bond, okay? So knowing your trend in electronegativity, it can help you out of a tight spot if you're not really sure what a dipole looks like. Okay. Now, in terms of charges, this is our OH minus. The the lone pair is on the oxygen here. Okay, this is what's making it a nucleophile. It's really the lone pair, because ammonia is a nucleophile as well, because the nitrogen's got a lone pair on it. Okay, even though it's not fully negative, it hasn't got a negative charge. Okay. It's got that lone pair, and that can make it a nucleophile as well. Okay, it is a nucleophile. So when you're asked what a nucleophile is, okay, it is an electron pair donor, okay, or an electron-rich species that can donate a pair of electrons, okay? It doesn't have to have a negative charge in it. Now, that's lone pairs. Now, lastly, curly arrows. Very importantly, okay, it shows the movement, or they show the movement of a pair of electrons. If you're ever asked that, okay, don't just say it shows the movement of electrons. It's the pair of electrons. And because it's a pair of electrons, one of two things is always happening when you draw a curly arrow, okay? When you draw a curly arrow, it's either one, a new bond, a new covalent bond formed, so you're making a new covalent bond between two things, or a covalent bond is broken. That's the only two things that can happen when you draw a curly arrow up. All right, either you're forming a new bond or you're breaking a bond. Okay, now very specifically to this bit, if you're breaking a covalent bond, it is heterolytic fission. In other words, that pair of electrons, both of those electrons in that pair go to the same atom. Okay, that's what heterolytic fission is. Every time you break a bond, it's heterolytic fission, apart from free radical substitution. That's where you get your free radicals. That is homolytic fission. Okay, but every curly arrow you draw to break a bond in a mechanism is heterolytic fission. Okay, the only example of homolytic is where you're forming that free radical in UV light to split that chlorine molecule. Okay, so let's talk about the story. Now, you could just remember the mechanism, which is okay, but they're not going to give you the example you use to remember it in the exam. Okay, you've got to work with the different substances that they give you. So the first thing that's going to happen here is that obviously overall, because we know it's nucleophilic substitution, we need to swap this chlorine out for the OH. So what's going to happen is, remember, because the curly arrow is the movement of a pair of electrons, it is never going to be from the carbon to the lone pair. Because if we're showing the movement of a pair of electrons, well, what we're saying here is because this is delta positive, it hasn't got any electrons to share. You know, there's nothing there, okay? Electrons have to move from where there's more of them to where there's fewer of them, okay? That's what happens with electrons, okay, when you draw in your curly arrow. So that's one thing to hang your hat on, a logic thing. Electrons move from where there's more of them to where there's less of them. That's showing the movement of electrons, okay? So, you know, it's a case of if you drew the curly arrow the wrong way, well, there aren't any electrons here to move, okay? So it has to be from the lone pair specifically to what they're attracted to is this delta positive carbon. So that first curly arrow there, I am forming a new bond, okay? I'm forming a new bond. That's why I'm drawing that curly arrow there, to form that new bond. But the story goes, well, carbon now, technically, because I formed a new bond here, that's now got 5 bonds around it. That can't happen. Carbon's only got room for 4 single covalent bonds, or 4 electron pairs around it. It's in group 4, right? So that's the maximum number of covalent bonds it can form. So something's got to give. Now, if you remember what I said before about bond polarity, if a bond's polar, that means it's weaker. And because this bond is the most polar one, that's why this pair of electrons moves to the chlorine. We're breaking this bond now, okay? Because it's polarized, it's weaker. So the OH comes in, just basically bullies the chlorine out, okay? So we're forming a new bond with this curly arrow, and because that new bond's formed, as a consequence, this bond has to break. So you can see we're going from the bond here, this pair of electrons, to the chlorine. And because the chlorine is the most electronegative, that's where those electrons are going to go, right? Chlorine, we're spending most of our time with chlorine anyway. We may as well just spend all of our time with chlorine, okay? So as a consequence then, this is all just a one-shot organic mechanism. There's no intermediate with this one. We end up with our COH, excuse the rubbish drawing, plus our Cl minus. Now this is negative, the reason being because it's taken a pair of electrons with it. Remember, one of those electrons in this CCl bond actually belonged to carbon. So it's had off with one of carbon's electrons, but carbon's happy because it's been, you know, given an extra by the OH here, okay? So because this chlorine disappears with this pair of electrons, that's why it's fully negative, and this lone pair is the pair of electrons that it took from that covalent bond away with it. Okay, so tell yourself the story whilst you're learning these mechanisms. Tell yourself the story, and it's much more memorable than just trying to photographically memorize these individual mechanisms, okay? Even write the story as you're learning the mechanism, okay? Saying what happens at each stage. So what that does is it instills an understanding of how the mechanism works, as opposed to just parrot fashion learning where the curly arrows go. That is going to let you down in an exam. 100% it's going to let you down in the exam. So just make sure that you tell the story. Write it down. You don't have to do it every time, but just write it down once as you're learning them, okay? I got 2 more things to show you and then I'm done. And I say show you, tell you. When you're learning mechanisms, another piece of advice, let me just kind of focus in on me for a second. Another piece of advice is that when you're learning your mechanisms, learn them in groups of mechanisms. Don't learn them individually, okay? Especially like AQA. AQA, you've got more mechanisms to learn than anybody, all right? Group them together. From memory, I think you have two different electrophilic addition mechanisms, okay? All from alkenes, of course. Is the only time you're going to get electrophilic addition. Those are basically the same mechanism, just slight tweak, okay? But it's certainly the same family. It's the same mechanism, electrophilic addition. You've got 3 nucleophilic substitution reactions, okay? All hovering around the haloalkane. So I think you have to make an alcohol, so that's an OH. You have to make a nitrile, which is obviously a CN minus. And you have to make an amine, which is an NH3, attacking the delta positive carbon there. But they're all the same mechanism, okay? Slight tweak on the ammonia one, okay, because there's an extra step, but essentially the same mechanism. So they don't treat them individually, group them together. Likewise, and this is for everybody, benzene, if you're doing A-level, okay? There's one mechanism for benzene, okay? Electrophilic substitution. It is the same for every single one you need to do, okay? It's the same mechanism. It's just all you've got is a different electrophile. What's the big difference in that mechanism there, or between those mechanisms, whether it's nitration, alkylation, acylation, or halogenation, like all of the Asians, it's the equation to form the electrophile and the equation to reform the catalyst. They're the important things to remember. If you remember the mechanism in the middle, it's basically the same for all of them. It's just you're replacing the electrophile, okay? Instead of X minus, it might be NO2 minus, for example, okay? So group your mechanisms together whilst you're learning them. Now, one last thing to show you is that, and it's more about A-level nowadays, okay? Hey, Tariq, we're just about finishing up, but hello. One last thing I want to show you, and I've done a TikTok on this before, and that is the rise of the unknown mechanism. So in recent years, all of the exam boards have started putting questions into the exams. In the main, admittedly, A-level, but it's not beyond them to put in an AS exam as well. Not that many of you do AS now. But what they're doing is they're putting mechanisms in that are not in the specification. They might be very similar to what's in the specification, but they're not in the specification. They're not mechanisms you've learned. And over the last few years, well, every year I've had a student or students come up to me like, oh, my days, like, what the hell's that doing in there? Oh, you know, we're not supposed to know that. It shouldn't be in the exam. And you see them on social media going nuts about it. But you know what? Nobody ever said that couldn't happen. They're not asking you to do it from scratch. They're asking you to work it out. Okay, and I'll give you an example. What they're doing this for is to, I think they've cottoned on over the years that students are just parrot fashion learning these mechanisms, not really understanding the content. But of course, the examiner's job is to make sure and test you on your understanding of the subject. And that's why they're putting these mechanisms in now, okay, especially over the last 2-3 years. So let's show you. So this is a selection of what I call unknown mechanisms. So this shows the incomplete nucleophilic addition mechanism for the reaction of water with chloroethanol. So this is an A-level one, nucleophilic addition. We should remember that this is the reaction that we classically see that is in the specification between an aldehyde or a ketone and a CN minus ion, okay? So we make a hydroxynitrile through nucleophilic addition. Don't worry if you're AS, I just want to show you this, okay? So what they're doing is, they're asking you to complete the mechanism by adding 2 curly arrows, all relevant charges, and any lone pairs of electrons involved, okay? Now, when you get something like this, these unknown mechanisms, you don't stand a chance if you've just parrot fashion learned the mechanism for nucleophilic addition, because it's not exactly the same. Understanding how the mechanisms work, that is what's going to get you these 3 marks, okay? So we can see here that this lone pair on the water is attracted to this carbon. Now, it's instructed us to put all relevant charges and dipoles and things, okay? So if this lone pair is attracted to this carbon, that must mean, and I'm just going to make this a little thinner so I don't go mad, that must mean that is delta positive and this is delta negative. And we know this anyway because oxygen's more electronegative than carbon. We know a carbonyl group, a C double bond O, is polar. Okay, so we formed a new bond with this curly arrow, which is, hello, this new bond over here. This double bond here has broken. So this pair of electrons in this bond that's breaking has now moved to the oxygen. So what we need to do is, okay, there's the one bond that's left over. We need to add some charges and some lone pairs and some curly arrows here. So let's do that first. Let's start with, okay, so technically this lone pair, okay, they both belong to that oxygen. As soon as this oxygen bonds to this carbon using both of its own electrons, then this becomes positively charged. Why? Because this pair of electrons it did have, because it's now sharing technically one of those electrons that was its electron, now it's using both of them to bond to carbon. Technically now, one of those electrons now belongs to carbon, because that's what a covalent bond is, right? I know we're forming a dative. This is the formation of a dative covalent bond, but it's still just a covalent bond once it forms. It's just how it forms is different. So technically one of those electrons that did belong to oxygen now belongs to carbon. So that's why technically we can say that oxygen's lost an electron now. That's why that's positive. On the flip side of things, this pair of electrons that was in this C double bond O, where the bond broke, both of those electrons went to this oxygen, and that's why that now has a lone pair on it. And because it's got a fully lone pair, remember, this pair of electrons here, one of them belonged to carbon. So it's had off with an extra electron. One of those electrons belonged to oxygen anyway, but the other one belonged to carbon. So now this oxygen has an extra electron. It's pinched one of carbon's electrons, so that's why it's fully negative. Okay, so that's where we end up with our intermediate here. Okay, let's get rid of these. We don't need that. But we end up with a lone pair and a fully negative charge and a new bond and a positive charge on the oxygen below. Okay, now we need to add curly arrows and we need to play spot the difference. So what you'll notice is that spot the difference here, this has changed. Okay, so what's happened here is that this oxygen is no longer positive. It's just an OH group, okay? But we have lost, we have lost this hydrogen. So how did we lose this hydrogen? Well, this hydrogen here, look at this. It's become a H+. So when this hydrogen to oxygen bond broke, the electrons didn't go with the hydrogen because this is just a proton. So those electrons must both be with this oxygen now. So as far as this bond breaking is concerned, this pair of electrons both moved to this oxygen, which fixes our problem of a positive charge and leaves us with a hydrogen ion that's left. Okay. Now, the other part is basically the same. We've still got a lone pair and a negative charge. Okay. So that's where we're up to. So there's one curly arrow. They asked us to put two in. There's one of them. Now, where does the other curly arrow go? Well, let's play spot the difference, but this time between these two. So we know that this H must have joined this O to make that OH. Okay. So where does our curly arrow go? Well, we know that forming a new bond, okay, we need to take that pair of electrons and show where they've moved to. So that pair of electrons moves to this hydrogen, and that's what forms these OH bonds. So if you get these, especially A-level students, okay, thanks, Akari. If you get these in your exam, especially A-level students, you've got to understand the story of a mechanism. You've got to understand exactly what a curly arrow shows. You've got to apply a bit of logic here. So just learning your mechanisms parrot fashion is not going to cut it nowadays, ladies and gentlemen. Understand the stories, and then when you get something like this, They will be kind. They will give you a structure. You can see with these other examples, okay, there's one here where they've given you a structure. You need to be able to work that out. There's one here where they've given you a structure. You need to work it out. That was a horrible one from OCR. This one here is AQA again. But again, they've given you the structures to work it out, okay? And this one down here, you got to figure out like, okay, well, that oxygen must now be bonded to that carbon, and you know, that carbon must now bonded to that oxygen, and that oxygen must now, yeah. So you can work it out. So what I'm saying is, understand your mechanisms. Don't just learn them, okay? So that's us for today. Hopefully you found that useful, guys. So what we've covered is atomic structure, and it's linked to basically so many other areas in chemistry. So those trends and those patterns and things like that about redox and about electronegativity and so on and so forth, they all link right back to atomic structure, okay? So these unknown mechanisms, where can I put them? I will put them in the comments as soon as I'm done on this video. I'll put the link to these unknown mechanisms in the comments for you, okay? How's that sound? Okay, do they have the mark schemes with them? No, there's no mark scheme with them. So I don't know how useful they'll be to you, but I'll put them in there anyway, okay? Any advice for structuring our revision for chemistry? So, Hafiza, you, well, past papers. That's how you structure your revision, okay? Think about it this way. A lot of the time, students are like, I need to revise, I need to revise, I need to revise. When are you ready to do past papers? Like, how long's a bit of string? You know what I mean? Like, how long is a piece of string? Like, how long do you wait, okay, before you start doing past papers? Generally speaking, in my experience with students, too late. All right. The first thing you should do is sit down and do a full past paper in time conditions. Because otherwise, once you mark it, how else are you supposed to know what areas you need to work on? How else are you supposed to know? Okay. Thank you, Akari. Otherwise, right, two options if you don't use past papers to dictate what you revise. Okay, because the way you improve on anything is by looking at your weaknesses and fixing them and improving them. That's how we get better at anything, okay? You know, that's how we get better at tying our shoelaces when we learn how to do it. There was always one bit that maybe you couldn't do. You just work on that bit over and over again, okay? Otherwise, you've got two options, okay? If you don't use past papers to inform what to revise. Your two options are revise everything. Not an option, right? Because you spend a year, depending on what year you're in, a year or 2 years, learning all this content, okay? Yes, you probably need to brush up on the stuff you did back in September to Christmas, maybe, okay? But revising everything is just not an option because you just do not physically have time. I don't care who you are, it is absolutely impossible. The second option is you just pick. What are you picking based on? Oh, I feel like doing some inorganic chemistry today. It was like, well, do you need to do inorganic chemistry? Are you doing that because it's your favorite? Nobody ever chooses things because it's their least favorite. And classically, your least favorite topics are the ones that you're probably worst at because they're your least favorite, or they're your least favorite because you're not very good at them. Either way, it's self-fulfilling prophecy. So your two options are do everything or just randomly pick. Just like, you may as well close your eyes and just pick one at random, okay? So structuring your revision is all based around past papers, because how else are you supposed to know what to do, okay? Oh, speaking of which, let me show you. I tried to show this yesterday. So the AIs I've been working on, I am so proud of this, right? Let me show you. So yesterday I tried this, right? And because it had updated in the background to a different Gemini, the instructions I gave it like weren't doing what I wanted it to do. So just check this out. So this will do anything, okay? And it's linked directly to your specification. So if you're a Chemistry Coach member, this is basically your study buddy. It will do anything. It will write questions for you. It will teach you something, okay? It will mark work for you, all based on your specification. It tells you nothing more that you need to know, okay? So for example, if I just write something like, where are we? Whoop, not yes. So test me on the definitions of enthalpy changes that I need to know. So if you're trying to remember the definitions for delta H's, boom, you put that in there, and hopefully, I tried this live yesterday and it screwed me over, but hopefully this will give me exactly what I want. So we will think about it for a little bit. There we go. Okay, so what it'll do is it'll give you the questions and then give you the answers that follow on down there. So you don't need to ask it twice to do it for you, okay? So what we can also do is write me this is what I tried yesterday, exam question on a calorimetry, I can't spell, practical, provide answers and explanations at the end. Okay, boom. So if we do this as well, what it should do is provide us with, it can't generate pictures. That's the only downside here. But what it will do is give you a structured exam question and the answers at the end for whatever you want it to test you on. I'm pretty sure if you asked it to write a test for, let's say, your OCR module 2, write me a 30-mark test on module 2. It will do it for you and give you all the answers, okay? So they've given a setup here and everything that you need in order to produce this calorimetry practical, and it'll ask you questions on it. So you need to use the data like you would in an exam paper in order to do that, okay? So it's phenomenal. I'm just going to just press one of these buttons at the top here, walk me through, where are we? Is he going to do it? Walk me through the process of recrystallization. Okay, so the recrystallization pack is hugely important in organic chemistry. So what it's going to do there, here we go. Okay, dissolve the impure solid, very soluble at high temperatures, but ensures there we go. It's letting me down again. As soon as it's live, it starts getting shy. This, I can't believe this is happening. So this will work for you, okay? Even if you say, give me a study schedule for, I've got I need to revise X, Y, and Z. Write me a study schedule to learn all the most important parts of the topic. It will absolutely do that for you. So it's a really, really useful tool to help you when you're revising, okay? So I will leave you guys to it. Tomorrow it's onto A-level stuff, okay? So tomorrow and Thursday, Wednesday and Thursday, all about A-level stuff. And I'm just here to give you a broad version of that. Now, if you want to become a Chemistry Coach member, you can do so. I'll be coaching all the Chemistry Coach members right the way through to the end of the exam. So once a week, we'll be looking at skills and exam technique and exam strategies. It's not tutoring, okay? You've got all access to all the information you need, but I will be doing open questions and stuff like that at the end of each session. So that's cool too. But I'm there to kind of help build your experience and your tactics, if you like, and help you get more marks out of what you already know. That's what coaching is, okay? Getting more marks out of what you already know in the exam, okay? So I will love you and leave you guys. Thank you so much for coming along and joining me. And if I don't see you here, maybe I'll see you inside the Chemistry Coach course, and maybe tomorrow, again, live on YouTube. See you later.